So I think we can slowly start. 3 o'clock. Good afternoon, everyone. Welcome to our talk with Geronimo Ortula about the backup of the world's largest machine. Let me present Geronimo. Geronimo is an automation engineer. He has been working at CERN the latest 15 years, most of them as a part of an expert team that provides support and standard solutions to the whole CERN industrial automation users community. In 2015, Geronimo conducted a market survey to find a solution for automatic backup of control systems, and finally set up a service based on versiondog, which is currently used by more than 150 users at CERN. What is CERN? CERN is the European Organization for Nuclear Research in Geneva, Switzerland. My name is Helmut Wollersheim, and I'm Key Account Manager at AUESI. Let me introduce our agenda today. Working with CERN and in person with you, Geronimo, since 2016, we have asked you to present CERN here, to learn how you work with the Large Hadron Collider, LHC, and to understand how you handle the data management in the industrial automation at CERN to make sure there will never be a data loss which may cause an expensive downtime. By doing so, we hope to give you both a good insight in the world of CERN and in the role of versiondog. Before I hand over to Geronimo, just an organizational hint. As our time in this webcast is limited, we have about 45 minutes. Please write down your questions directly here in the chat. If you have enough time left at the end, we will answer some of the questions directly here. In case there is not enough time, we will pick up your question and prepare a question and answer paper for you. Thank you. Geronimo, the floor is yours. What are CERN's mission and impact?
Thanks a lot, Helmut and AUESI for inviting me here today to this event, in which to give me the opportunity to talk a little bit about CERN, to show our audience what we are doing. And I've prepared a very short presentation in which I will give you an overall vision about what we do, and then I will talk a little bit about control systems as well. Okay, so first of all, what is CERN? CERN stands for Conseil Européen pour la Recherche Nucléaire, so it's the European Laboratory for Particle Physics. It was founded in 1954, so more than 50 years ago, and it's composed by many people. I mean, we have contributors from more than 110 nationalities all over the world, and from more than 70 countries. Okay, so we say it's the largest particle physics laboratory in terms of contributors and also in terms of budget. So we have more than 1,000 million Swiss franc budget per year. And all this is public money, is financed externally by the member states or by external organizations, institutes, and academia. Okay, so personally, you see here some of the numbers regarding staff, fellows, associates, students, and we have more than 10,000 users coming from many different institutes and companies. So around 2,000 external companies are collaborating with CERN. Okay, it's composed by 23 member states, mainly all of them in Europe, 6 observers, 6 associate member states, and 2 associate member states in pre-stage of membership, meaning they would like to be part or to be member states of CERN. Okay. So what is the CERN mission? So what we do here is fundamental research. Part of some people think because of nuclear research that we do nuclear development. Well, probably nuclear is in old term. Now we talk about particle physics. we do fundamental research, we do physics, okay? And the aim of CERN is to understand what is the universe made of and how it works. And for this, basically, we study the physics laws that give information about what is the matter made of, okay? From in order to understand what is the matter made of, there have been many theories. The human being started to study the matter like a long time ago in the 4th and 5th centuries, like stating what would be the atom, and then later on in the 19th century, establishing what would be the structure of the atom, the electrons, the nucleus, and then beginning of the 20th century, it was understood what the nucleus was made of, protons, neutrons, and other particles. And in the 60s, with new accelerator, with new machines, we were able to understand what the inner composition of the nucleus and the theory of quarks and other particles. And now CERN is trying to continue this research into the future, understand what are other kind of particles, or the interactions that explain what the matter is made of. Okay, for this, we need to build accelerators. Okay, we need to build accelerators in order to give energy to those particles so that we can make them interact. What we do at CERN is basically collide particles. So we made them interact between, it could be another particle or it could be a target, so that when they collide, they produce interactions, and studying those interactions gives us a lot of information about what matter is made of and the different laws of the physics that are involved in that. Okay, so we need accelerators, we need particle detectors that are basically the machines that are recording every single thing that's going on when a collision is happening. And also we need all this data that come from the particle detectors. We need to store it and analyze it. And for this we have a grid. Grid is a big structure of collaborative structure of many institutes that they provide computing power and storage in order to store all this data and to be able to analyze those data. Okay. So building an accelerator is simple. We just need a couple of screws and the instructions, and anyone can do it at home. So you feel free to try. And we did it at CERN. We started in the 50s. So it was the first one, the proton synchrotron in 59. It was a 630 circumference circular accelerator, which could reach to an energy of 28 giga electron volts. Okay, then a few years later, 76, it was commissioned the super proton synchrotron. Oh, okay, so it was bigger, like 6.9 kilometers circumference, and also bigger in energy, 300 giga electron volts. Okay, then later it was upgraded up to 450 giga electron volts in 81. Okay, we continued building big accelerators. In the 80s, it was the phase in which the Large Electron Positron Collider, the LEP, was designed, and it was in operation from 89 to 2000, 11 years. That was an electron positron collider. It had 27 kilometers in circumference and collisions at 2 times 209 giga electron volts. That infrastructure, the tunnel for the LEP, was used but reused in order to install in them what's today the Large Hadron Collider, the LHC, okay, which is the biggest accelerator today. So it was designed between 1994 and 2008, 14 years of design. The operation started in 2008 and it's still in operation, okay? And we want to operate it still another 20 years minimum, okay? It's a proton-proton collider. It has 27 kilometers as the LEP, so it uses the same tunnel. And it produces collisions at 2 times 7,000 giga electron volts by means of superconducting magnets. I will talk later on what are the technology principles in an accelerator, but basically we need superconducting magnets, and for this we need superconducting materials that reach the superconducting conditions at minus 271 Celsius. Okay, all these accelerators that I've shown, they are part of the CERN accelerator complex. Okay, they are all in use except the lab. The lab, it was decommissioned, and then we used the same tunnel to install the LHC. And now all the accelerators that you can see, they are part of the accelerator complex. And this is like the gears of a car. You have a particle that you need to accelerate, and then you do the accelerator in several stages, okay, using different accelerators with different power. So all starts in this little bottle of hydrogen. Okay, you see the hydrogen there. So then from the hydrogen, we extract a proton, which is a positive particle. We extract it and we inject it in this LINAC 2. The LINAC is linear accelerator. Okay, it's basically electrical field that is able to move a positive charge particle into it. Okay, so the principle is very simple. We move it, and then we start accelerating that particle linearly, and then we insert it into this booster. This is a circular accelerator that starts to push the particle into it, and then it starts accelerating the particle. Whenever the power needed to go to the next stage is reached, then we inject it into this transfer line that makes this proton to go into the next accelerator, the PS, the positron synchrotron, that is used to accelerate to reach a higher level of energy, 25 giga-electron volts. As soon as we reach this level, then the proton is transferred into the SPS, 7 kilometers. Okay, and then when we reach this 450 giga-electron volts, then the beam, the protons are transferred into the LHC via this way. So they will turn into this direction, or this way. So they will turn in the opposite direction. So in the LHC, we have two beams transporting protons at very high level of energy, which is 14 tera electron volts, and in opposite directions. Okay, and then we collide these two beams in two different points in which we have 4 detectors. Okay, these points are ATLAS, ALICE, CMS, and LHCb. The detectors, as I mentioned before, are the machines that are able to detect and record every single event that is happening when a collision is produced. Okay, all this is built underground to protect the interactions from the external conditions. Okay, so it's built 100 meters underground. And the principle of the accelerator, the technology that we use in accelerator is quite simple. It's two things. The first thing is a radio frequency cavity, which is basically a device that allows to speed up a charged particle by alternating electrical field. So if we have a proton here being in this cavity, so when the proton is there and is close to this negative field, then it gets attracted, and then whenever the proton goes right in the middle, then the polarity changes, and then the proton gets pushed into the next cavity, right? And then just producing sending the proton through all those cavities that are alternating the electrical field, then you manage to speed up the proton. Okay, so we use radio frequency cavities to speed up and to transfer energy to the beams, and then we need to bend. Since we are in a circular collider, we need to bend the trajectory of the proton, and for this we need magnets. We need a magnetic field. The proton is charged, okay? So we need a magnetic field that is able to bend the trajectory, to change the trajectory of the proton. Since the proton is at a very high level of energy, we need a very power magnetic fields. And to produce a magnetic field, we need a coil and electrical current going through that coil, okay? In order to produce the magnetic field that we need to bend the particle, we need 3,000 amps of current. And you can imagine that at 3,000 amps, any kind of no conductor is able to hold this current. So we need other kind of technology, which is the superconducting materials, that are special materials that they operate at a very low temperatures, because they have their superconducting properties at very low temperatures. And those temperatures are 1.8 Kelvin, is minus 272 degrees, okay? And this is one of the challenges of LHC, is not only operating a high currents, high magnetic field, but also low temperatures. So we are talking about the largest accelerators. You have here a picture in which we see here the Geneva airport. This is the border, and then here we have the layout of the accelerator. This is the SPS, okay, and this is the LHC 27 kilometers, 100 meters underground. We have two sites. This is the Meran site, and this is the Prevesant site, and then yeah. So here we have the collision points here, there, and there. Okay. As I said, we have for the accelerator thousands of superconducting magnets. Okay, and then we need minus 271 to operate superconducting magnets, and this requires a lot of power on cryogenics, on producing cold. Okay, that's why we call it the coldest place in the universe, taking into account that the average temperature of the universe is 269, something like that, minus 269. We call it the coldest place in the universe. Also, we like to say is the coolest place in the universe. Okay, so then these are the 4 detectors that I showed. So the 4 collision points in the accelerator: Atlas, ALICE, CMS, and LHCb. They all look at different kind of collisions. Atlas, for example, is 22 meters times 44 meters. So you see the scale. Looking at this person here is 7,000 tons, and there have been 2,500 people involved, 167 institutes. CMS is the second biggest detector at CERN, 16 meters times 21, and also you can see that you can have the notion here of size by looking at that picture. Okay, so just to mention that in July 2012, it was one of the most successful moments at CERN, because, well, both experiments saw something that it was finally announced as the Higgs boson, that was announced in 4 July 2012, and well, this resulted on the Nobel Prize for Peter Higgs later on. Okay, I mentioned before about grid computing. Apart from accelerating particles and then making particles collide and then being able to understand what happens in the collider, we need to treat all this information. We are talking about 600 million collisions per second. What's going on in the LHC? Okay, we are talking about 150 millions of sensors installed, 150 collisions per second stored, because we don't store all collisions. We separate, or we reject some of the collisions that are not best quality. But this results on a final 800 megabytes per second, more or less. And for this, we need a lot of storage power. We store around 10 petabytes, which is 10 million gigabytes per year. And for this, we need computer centers. Okay, we have one big computer center at CERN, which is equipped with 230,000 processor cores, 1,500 servers, and then we collaborate with grid computing with a network of 170 computer centers in the world. We share computing power, computer storage.
I have a question. May I ask a question?
Yes.
Here you mentioned that CERN does fundamental research, and I think it was all about that now. What
Yes.
about further research? Do you have side products or whatever, things what you discover while working on the fundamental research?
Well, at the level of the fundamental research, most of the things I mean, the result of the research is to understand how are the laws of the physics, right? And this helps quite a lot to understand many things that are happening nowadays in many aspects. And also, well, for the future, we are preparing like an upgrade of the current accelerator that it's foreseen to operate two times the power that it's operating now. And also we are trying to increase the luminosity, which is the number of events that you can have per second. And also we are working on the design of a future bigger accelerator. This is on the design phase. We don't know yet if we will have the money to build it or they will be built, but the design is ongoing, and it's foreseen to be a 100 kilometers accelerator. Okay, and then regarding the impact on what CERN is doing in society, yes, we have some examples that I will give you later. I have prepared a couple of slides for that.
Great, thank you.
Okay, so then CERN is not only accelerators and experiments; it's also the biggest collaboration in the world. I mean, there are half of particle physics are working at CERN. The particle physics in the world, or are collaborating with CERN. We have a huge student program. So the mission of CERN is also to share the knowledge among the youngest. So we have programs in order to hire temporary technicians, engineer, doctoral students, summer students in physics. And we are collaborating with more than 100 countries. Okay. This is regarding what you mentioned, Helmut. So the technologies that we have been working with and evolving, these result on important inventions and important things that can be used by society. So we have many examples on vacuum, on cooling, on electricity, on cryogenics, on medical applications, accelerator used for other purposes like imaging, detectors, thermal energy, and so on. So I will give you just a few examples. For example, World Wide Web, that this is the result of something that was it was the result of people that were working at CERN in the 80s, and they decided to, or they managed to get a way to share information in Ethernet, and they developed World Wide Web, which is now commonly used by everyone. Also, we have a lot of impact on, for example, in satellite imagery. We have pixel detectors that are basically photon detectors, and they are used for satellites to have high resolution images. For medical applications, as I mentioned, we are able to use protons to kill some tissues of places in the human body that is very difficult to access. And also we use accelerators to produce images like you see there in the slide.
Yes, this is exactly what I meant. This, you can call it maybe collateral side effects.
Yes, spin-offs, we call it.
Yes. And what about the dimensions of the industrial automation at CERN?
Well, it's so you see CERN is very big. We have a lot of facilities. We have the accelerator complex with made of different sub or smaller accelerators. So at the end, the services or the different processes that we need to maintain in order to be able to run all this are a lot. So you see from cooling and ventilation, vacuum in order to maintain vacuum into the beam pipes, so that we can we can move the beams. We have the detector control, so all what's going on in the detector, we need to make sure that it's operating at the nominal conditions. Cryogenics to produce the necessary cooling power to cool down the magnets to 271 negative Kelvin. Gas distribution for mainly used for the detectors. Environmental radiation, this is very important. So there's some small radiation produced by the accelerator. So we are constantly monitoring in the environment all these parameters. Also, we have controls for the electrical grid, a lot of controls for interlocks and safety, and many others related to computer centers and many other things. Okay, so we have to cover many different processes and many different challenges because of those processes. The main challenge regarding industrial controls is the availability. Okay, so LHC is working 24/7 and all the time, is never stopping. So we have several times during the year in which we stop the LHC for maintenance, but while it's in operation, it never stops. Okay, and so we need to ensure that all the systems are working and operating all the time. Okay, so this is a challenge, availability. And then another challenge is certain things that are not common to general control systems, like, for example, environment. So we have to deal with radiation areas in which we have to control several things. So we have to build our own devices so they can operate on radiation areas. Large system, highly distributed or interconnected. So many times we need to interconnect several control systems. Complexity, many times the behavior of the process is not foreseen. We are talking about systems that in most cases are commissioned for the very first time, and we don't have any experience on the dynamics of the process. Also, we are talking about precision. So many times we need to do a very precise measurements to make sure that we deal with the parameters that are required. And performance, we need to make sure that all what happens is according to what we expect. Okay, this especially for regulation, which is a very common in industrial controls. Okay, and this is an schematics of our architecture and some figures about what we have regarding industrial controls. So regarding the different layers, on the top we have the SCADA layer, the visualization, business logic, archiving. There we have 600 SCADA applications to cover most of our control system, 400 industrial PCs to host all those applications. We are using Oracle databases, and we store process data at the level of 200 terabytes per year. Okay, in the control layer, we have different devices. We have up to 2,200 PLCs. We are using OPC UA as technology for communication. We have 200 OPC UA servers, and we use industrial PCs also at the level of control. Real-time front-end computers, 60 we have nowadays installed. And then on the process layer, we have many devices, hundreds of power supplies, field buses, and around 10 million IOs overall our control systems. Technologies, well, on the top we are using WinCOA from Siemens, Oracle. On the control system, PLCs from Siemens, from Schneider, OPC UA, Siemens Simatic IPCs, and then on the process layer, we are using many different technologies for field buses, Modbus, WorldFIP, Ethernet IP, Profibus, Profinet, CAN, for CAN gateways, SysTech, ANAGate, and high voltage and low voltage power supplies, and so on. So just to give you a notion of what we have, this is cryogenics. This is one of the most critical control system at CERN, because we need to provide with the temperature needed to the magnets to operate. So we are talking about 27 kilometers of decentralized instrumentation and control, because we need to act on the process along the LHC on the 27 kilometers. We are talking about 50,000 IOs, 11,000 actuators, 5,000 control loops. We have around 100 PLCs and 40 industrial PCs, and we have 26 SCADA applications for a total of 1.5 million tags, million variables that are coming from the process. Okay, this is just to give you a bit of a notion. So that's it from my side. As a summary, just to say that, yeah, we are an international collaboration. We believe and we work for fundamental science. So is a research institute. We just do research, and also we are very proud of the impact on society of the technologies that we produce here, how they impact on society. Thanks a lot for your attention.
Thank you very much, Geronimo, for this presentation. We see that this is a real impressive and fascinating world, and I do think it is justified to call it world at CERN, with more than 2,000 PLCs and 150 users. I can say we do not have this every day at versiondog.
Yeah.
I would like to ask you, Geronimo, in your personal introduction, we said you are using versiondog since 2016 after having conducted a market survey to find a solution for automatic backup of control system.
Yes.
So why did you search for a solution like versiondog? What exactly was your motivation further than the mentioned functionality for automated backup?
Okay, you know, at CERN is very big. So CERN is like many different companies all together, right? So we have many different what we call equipment groups, and the equipment groups, they have their own people taking care of their own control systems. Okay, so that we are ability for we have to make sure that all the equipment groups work in the same way. We saw that there was a lack of methodology and discipline in the way, for example, backup of applications of PLC applications in productions were managed. For example, you have a problem in a PLC, and then you have to replace the CPU. You need to load the PLC program, and then there was a problem because you didn't know what was the latest version. You don't know what is the current version, and so on. So there was a lack of methodology on some equipment groups and discipline. Also, some groups, they had their own procedures that were in some cases complex and difficult to follow. And so what we thought as a central group that we provide CERN-wide support to all the PLC users, we decided to propose a service based on central access, full availability of the whole PLC applications at CERN. And that was the motivation, was to fix this, or to be able to provide a solution for this kind of problems that at the end were causing human errors. The fact that after an incident, we were not able to recover easily the application, the software that was running into some of the PLCs. Okay.
So you were looking for a more structured work stream to an all overview of your projects, and the thought also to have a higher efficiency, not to search. You needed a more transparent or bigger transparency of changes.
Yes, we want
search long for projects and so on.
Yeah, and also to provide central access, to have a central policy, to have common procedures for all the equipment groups, for the whole CERN users, so that they could access easily to all the PLC applications, and they could follow more or less all the same procedures, the same approach on the way they store their applications and they manage the changes on their applications.
Mm-hmm. Okay. What would you see as your most important benefit if you try to prioritize the first one or two most important things? What would you see there?
Well, I mean, to me, the most important benefit is to be able to tell at any time if what we have in the repository is with what corresponds to what it should be running in the PLC. Okay, this is the fact that versiondog is able to access online to the device and be able to make a copy of the online application and to be able to compare it with what it is in the repository. For us is a good advantage, is a major advantage, because it reduces to the very bare minimum the human error when managing the change of an application. Okay, and then also good benefit is the fact that, as I mentioned before, we have a central service, and this is very important at CERN, because, as I mentioned, at CERN is very big. It's very difficult to have everybody working in the same way. Okay, so by providing this service centrally, we manage to have all our users working in the way we think is the most appropriate and most efficient. Okay. Also, it helps the fact that, for example, the user interface for the versiondog client is very friendly and is very easy to use and very, very, very easy to understand. So the typical operations with the backup and compare, and then to have an overview of the different applications, this is very meaningful for the users, very difficult, very easy to use. That was also a very big advantage when we managed to get all the CERN users on board.
Great. So as you are the central point in CERN, that's kind of service provider for all of the departments. It eases your life also. It is more or less self-explaining. Yeah, when they understand and they don't need you so much.
Yeah. For us, it's very. I mean, for us, it's more efficient from the point of view of cost, and also from the point of view of the benefit for the organization to run services centrally. And then with versiondog, it was. I mean, we needed something that worked very well, and also something that was interesting for the users, because at the end they are the ones that are gonna use it. Okay, so that was the success of this. The fact that versiondog provided very interesting functionalities, and also the fact that we finally could build a central service for all our users.
Great. Do you remember any issue in the pre-versiondog time which was significant? I mean, like missing data availability, or yeah.
Yes, many. This is at the end. At some point, it became quite critical, because, you know, I mean, when for example, when the accelerators is stopped because there is a PLC that shut down, for example, or fails, this is an issue. Okay, because I mean, there are a lot of people behind that. It's expecting the accelerator to be restarted as soon as possible. Okay, so you can have many problems, but the problem you cannot have is that you don't know where is the backup copy of some of the applications. Okay, and that was the case in some cases. I mean, it could happen that yeah, you have a service, so that during the night, for example, they are called if there is a problem, so they have to intervene. For them, it has to be very clear where they can find the application that they need to install in case something goes wrong, right? And that was not the case. In some cases, well, they had to follow procedures, and as I said, the procedures were complex, were not easy to follow, and then they managed to get access to the repository, the previous repository, and then they don't find, or they don't know exactly what is the latest application that should be installed, and that was resulting on downtimes that we couldn't afford. So that's why there was motivation in order to improve at that level, and that's why the market survey was triggered, and then hopefully, well, we managed to find something that was fitting perfectly to our needs.
Yes. And how long could it mean that you couldn't proceed with your trials? Could it be a day? Could it be a week? Could it be a month?
When You mean if something goes wrong?
Yes, when you couldn't find the right project and
look, for example, at CERN, if there's something, I mean, if the accelerator shut downs, or for example, cryogenics. This is one of the most critical control systems. The cryogenics is 100% controlled by PLCs. Okay, if you have a problem on cryogenics, then you have to shut down the PLC, shut down the accelerator, the LHC, and then if you lose the conditions, I mean the cooling conditions after a few hours, for example, it could be 1 day maximum. After 1 day, then you lose the cooling conditions, and then you need to recommission the cryogenics again. So you need to cool down again the whole LHC, and this takes weeks. So that is critical. If you have a problem in one of the cryogenics PLCs and then you are not able to recover it in less than a day, for example, then the impact is really big, and it's something that it's really a problem.
So it is understandable how big is the impact due to versiondog not to have such kind of experiences.
Yes, and that's why also we have installed our versiondog instance. Well, we have a parallel server just to deal with availability of versiondog itself, but we have installed all our infrastructure, all the versiondog servers and the agents into a special cluster in our control room. It's a cluster with enhanced availability, which is powered with a special backup power, and it has a special availability so that we make sure that these services, this is one of the critical services at CERN, and is treated accordingly. And also we perform regular backups of all the information which is in the versiondog server, so that we don't lose, if ever we have a problem with the versiondog server, at least we don't lose all the backup history that we are producing.
Okay, so you sleep better nowadays than before 2000.
Yes, well, I don't have much problems to sleep, but yeah, I prefer to I sleep better. Yes.
Okay, thank you very much.
Thank you.
We are slowly coming to the end of our webcast. I would like to ask to marketing, Franzi, do you have any question which would be appropriate to discuss here? Did you see incoming questions?
Yes, we have got 2 questions. I can read it. The first one is, with versiondog, are you able to compare the previous versions, especially for CFC programming in Siemens PLCs?
I can answer shortly this question. Yes, we are able to do that. It's a standard application for us and no problem.
Okay, then the second one, for WinCC OA application, is it possible to locate the exact changes with respect to screens, icons or scripts, which has been changed with respect to any other version?
This is a little bit wider. Jochen, did you hear the question? Can you answer on that?
Not now, but we are able to answer these questions. It's not easy to explain this in a short time, but we will answer this question by email, so it's not a problem.
So thank you very much. So this is one of the questions what we are collecting now, plus a questions which will are still coming in. We will work now on this question and answer paper, which we will send via email to the participants in the next days. Okay, thank you very much everyone for attending, especially Geronimo. Thank you very much for giving us also the insight with your open answers on the questions in the last part of the webcast. Thank you very much.
Thanks for the invitation again.
You're welcome. See you next time, and I wish everyone a good SBS Connect fair still. Thank you very much. Bye bye.